So today we will continue our discussions on the emerging non-volatile memory, and today is about MRAM. So first we will talk about the principle of the MTJ, the magnetic internal junction. This is a key building block for the MRAM technology. And then we'll talk about three options for the MRAM technology, field MRAM and STT-MRAM and SOT-MRAM. So first of all, the MTJ. So this is the building block. No matter which MRAM technology you are talking about, this is a fundamental building block. So here we will have three layers, and in the middle we have this tungsten oxide barrier. So this is like a very thin tungsten oxide, and typically is like a MgO material. And then we have two magnetic layer, and then the bottom one is typically called a pinned ferromagnetization direction is fixed. So in this example, it's always pointing to the right. And then the top layer is called free magnetic layer. That means the magnetization direction could be switched between the left and the right hand side. So here you can think those are two little magnets, right? You have the North Pole, South Pole. And then when we read the cell resistance, we're going to apply the voltage across this stack. So we're going to measure the current going through this stack. So that is depending on this terminal current value. So here, if the two magnets have the same direction, then here the resistance parallel state will be lower than here when those two magnets have anti-parallel configuration. So we are going to depend on the resistance that is cross this stack to read out the memory state. So for example, if this is your 1, this is your 0. So here, those layers are very thin. Typically, here the MgO layer is just a few nanometer. And then, of course, those magnetic layers will be complex. We'll show that in the next few slides. But this is the principle. So basically, the bottom layer is pinned, and then the top layer could be switched depending on the programming condition. So we will talk about the right operation in the next as well. So here, actually, the real structure is pretty complex. Okay, it's more than what we just showed in the very beginning. That is like the principle. But in the real structure, so especially the bottom layers, there are many components to stabilize the pinned layer. So this pinning layer needs to be fixed. So therefore, there will be a lot of complicated materials deposited there. Most of them are like a ferromagnetic material, magnets, and it's very complicated. We will not go into the details of the composition. And some of those structure here is called the SAF, synthetic antiferromagnetic layer. So you need something here to stabilize, okay, this direction. And then here, then the barrier layer, internal barrier, is typically MgO. And then the magnets typically involve like cobalt, iron, boron. So that's a typical material. Of course, different designs or different foundries may have a little bit different composition. It's very complicated. But I think what you want to understand here is that we have those three key layers, and then there are many other layers to assist those three key layers. Those three key layers, as we showed here. So this is what you need to understand. at least for this course. Okay, so then this is mostly fabricated by the sputter, the PVD, the physical vapor deposition method, and you need a very precise control of the deposition. So it's not easy in terms of the fabrication. So let's talk about some device physics. So why would we have the high and low resistance states across the MTJ? This is all because of the quantum tunneling across that tunnel oxide. So here, because of the magnetic material, we have the spin property. You know, spin is some intrinsic property of the electron, right? So then here in the, let's say, parallel states, what you have here is that the density of states, you have the spin down and spin up states for the electrons, okay? So then if you have the voltage applied across this stack, then you will have currents, okay? But then this current depends on the tunneling of those electrons. But due to the Pauli exclusion principle, only the, let's say, the states that have the same spin direction will accept the electrons with the same spin states. So here is, let's say, the left-hand side pointing down, pointing down. So here we have a lot of empty states to accept the electrons from the down spin states to tunnel through the oxide. But if we have the anti-parallel state, then we are going to have the shift of the spin up and spin down, like you know, the empty available states. So you have this kind of DOS, density of states. So then the spin down will have less, okay, available density of states. So we will have less tunneling currents. So the magnetic material has this intrinsic property, which involves a symmetric, like the spin up and spin down density of states, essentially. So this is the fundamental mechanism. So here we are not going to go too deep into the quantum mechanics, but this is the high level to describe why we have different tunneling currents, even though the tunneling distance is the same. So here in the real experiments, what typically people will measure is this hysteresis of the MTJ resistance as function of the magnetic field. So at the end of the day, this is a magnetic memory. So if you apply external magnetic field, you're going to switch the spin, let's say the magnetization direction. So here, as I said earlier, so the bottom layer is pinned. So that means within this magnetic field, the bottom layer will not change. Okay, it always point to the right in this case. But the top layer will align with the external magnetic field, right? So this one, if you apply external field, then this one will align to the external field. And then if you reverse the external field, then you will switch to the other direction. So with different applied magnetic field, you can measure the resistance across this stack. Then you get this kind of hysteresis, right? And then if you think this is a lower resistance state, higher resistance state, then the ratio here, called the TMR ratio, is defined as the resistance change, the relative change, which means RAP, anti-parallel state, minus RP, parallel state. That is a delta R divided by the RP, the parallel state. Okay, so this is typically used in the MRAM. But actually, you can also think this is on-off ratio. So here, TMR 100% actually means on-off ratio is 2, right? Why is that? If the resistance, let's say RAP, is 2 kilo ohm, RP is 1 kilo ohm, right? Then here the TMR will be, let's say 1 kilo. Delta is 1 kilo divided by 1 kilo. Then it's 100%. But actually, here the on-off ratio is RAP divided by RP is 2 divided by 1, so it's 2. Okay. So 100% means 2 in terms of on-off ratio. So typically, the MTJ's on-off ratio is small. It's around 100% in most cases. Of course, then the community tries to improve the on-off ratio or the MTR, TMR. So here you see in the early days, when this phenomenon was discovered is in the 1990s. Initially, the TMR ratio is very small. And then with the improvements, especially when the ternal oxide layer is changed from the aluminum oxide to MgO, then the TMR ratio improve a lot. So initially people use aluminum oxide and later switch to the MgO. And even today for the commercial MRAM is MgO. Okay. So here then there are some papers even talk about super high TMR. It's like on-off ratio 5. So, but in most cases, if you look at today's commercial MRAM from the foundries, the TMR is like between 100% to 200%. That means the on-off ratio is like a 3 to 2. That's a typical value. Okay. So here, let's talk about the integration of the MTJ into the memory cell. So we need different mechanisms to switch the magnetization direction. So the first device that was integrated was called this field MRAM. Okay, so this is how it look like. This is the first generation of the MRAM. It's called field MRAM. And then the second generation is called STT-MRAM. We'll talk about that in more details, which correspond to this structure here. So let's look at the field MRAM first. So the field MRAM, the MTJ is here, and you need a selection transistor here. So the write operation is done by another wire that is underneath the MTJ. So and then between that there's isolation. So here in the middle you have like some floating or middle LAN. That's wire. That's interconnect. Okay. So the principle is that when you write the data, in this case, you are going to apply large current to the write word LAN. Okay. And then if you recall your middle school physics or high school physics, so here, if you have the current flowing through a wire, then what do you generate if the current, is changing? Then you will have the magnetic field around that, surrounding that, and then this is based on the what rule? Left hand or right hand? Right hand, right? So right hand rule. So that means in this case, if it's flowing in, then the right hand, then you are going to generate the surrounding magnetic field like this way. So that will align, in this case, that will align this free layer towards the right, in this case. If you reverse the current direction, then you're going to reverse the field direction. Then you can switch to the other direction. So here, the write is through additional word line, and you are going to rely on the field, the magnetic field, to switch. Okay, that's why it's called field MRAM. It's based on the magnetic field generated from your write word line. And then read is kind of decoupled from this case. Read is going to apply, turn on this selection transistor, you will pass current, and then you're going to read the resistance through this MTJ, and then you detect high or low resistance states. So that is the typical read. Okay, so there are some issues. We're going to discuss that in the next few slides about this field MRAM. So later, in the second generation, STT-MRAM, which is also the mainstream technology today offered by the foundries, try to get rid of this red word line. First, it will make the cell more compact. Second, this red word line, is not very efficient, right? You are going to pass a lot of current to generate the field and to switch. So in this STT-MRAM, then the read and write path shared. Okay. So in the write condition, you are going to apply the current directly through this MTJ to change the direction. And we'll talk about the details later, the physics later. But here you do not have the external field generated. Okay. The operation write and read is similar by applying current through the MTJ. The only difference is that in the write operation, you're going to apply large currents. In the read condition, then of course your current is smaller. So we'll talk about that in more details later. So let's look at the field MRAM first. Okay. Field MRAM. So this is like a cross-sectional view, right? So what you need to have is this, embed this red word line underneath the MTJ, right? And then you have your selection transistor here. Okay. So here are some real images from the early days. I believe in the early 2000, IBM spent a lot of efforts to develop this field MRAM technology. So there was a paper here from the IBM. And then here you see at that time, then the CMOS is large. And then here, this is MTJ, and this is the right word line. Okay. So here, the field MRAM suffer from the half select issue due to the disturbance. Okay. Because here you are going to apply the field, you need to select this cell. So your bit line and then the right word line needs to be turned on simultaneously to select this. It's like cross-point array, right? You have to select this cell. But then, since this field is generated surrounding this line, so the other cells along the same line will also see that field. So that causes this half select disturbance issue. Of course, here you want that only when you have two fields from, let's say, the right word line and then the bit line, when they intersect here, this field is large enough to switch the direction. But still, you will have the half select problem. So here, we are going to show some like improvements of this field MRAM design to somehow mitigate this half select problem. So this is called the toggle MRAM concept. So the key idea is that when you make the magnets there is always hard access and easy access. Okay, so what is that? So you know the magnet, you have to make it let's say the direction of the magnets in this case will be 45 degree respect to the word line and bit line, right word line and bit line. So let's say this is the right word line and this is bit line. So here you want to make the hard axis pointing next 45 degree. So that means here your orientation will be either pointing 45 degree this way or 45 degrees this way. You do not want to align that with the word line or bit line. So in this case, that means you will need both word line, right word line and bit line to be active to switch this one. So if you have another cell here, right? You have another cell. So you are selecting this right word line, but the BL, this one is not selecting. So you will only have partial field on this guy. So here actually it depends on the timing as well to suppress the half select problem. So for example, if you look at this schematic, let's say you are going to apply in the first case, you are going to apply the I1, which means horizontally this right word line, you are going to apply the current this way. And then you are going to flip this guy. And then here, in the middle, you are going to apply both I1 and I2. I2 means vertical currents. So you will further change this guy, and then you are going to flip this guy. So then in the final phase, you will flip more on this guy. And then finally, you are going to completely flip. So it depends on the timing. You can gradually flip the direction. So for the other half-selected cell, because you only have one of those currents, you will not be able to fully flip. So this is how you mitigate this problem. So here then, in the IBM's demonstration, here you see that 16 megabits MRAM, field MRAM, including the peripheral circuits, were fabricated. And the CMOS, underlying CMOS is 180 nanometer at that time. This is in the early 2000s. So here you see the die photo looks okay, I mean, overall. And then here are some performance, like read write time, like 30 nanoseconds. At that time, I mean, it was okay, it was actually pretty good. But there is a key challenge here. You look at the current, write current, or even read currents. 80 million for the write current. This is crazy, right? 80 million, huge currents. Right? Anything beyond million, you know, from the integrated circuit point of view, it's huge. Right? So here, this is because you have to, you know, generate this field. You have to pass large currents. So it's very inefficient in terms of the switching. So that's why this field MRAM never fly, even though it was demonstrated in the early 2000s. So then the industry switched to the STT-MRAM about like 2007, 2008 at that time. So here, let's compare what is the STT-MRAM. And so here you see conventional, this means field MRAM. You have this underlying word, right word line. And then actually here, the switching current is inversely proportional to this volume you want to switch. But then the STT-MRAM, we are going to apply the current through the MTJ. So the smaller the MTJ, the smaller the current. So here you see the scaling trend in terms of the MTJ cell dimension. As we scale the STT-MRAM, the switching current will also scale. But for the field MRAM, then the current will further increase. Because this volume is too small, then it does not fill enough external field. You need to further increase the current to get to insert more forces there, essentially. So it's too small, then it does not fill your field. Okay. So this is very difficult to scale. Then this current, that's why you need like tens of million, which is impossible for any transistor to provide. And also in the STT-MRAM, later you will see there's no half select issue. It's 1T1R array essentially, because the field MRAM is more like cross points. Even though you have the transistor here, but this transistor is only for read selection. For the write, essentially is a cross point here. That's why you have the half select issue. So for the STT-MRAM here, it's 1T1R for both read and write. So 1T1R, you do not have that half select issue because that transistor for the unselected cell could cut off whatever disturbance or sneak path. Okay, so then this is the early days of the STT-MRAM's research and development. As I said, in the early 2000s, then most of the demonstrations on the chip level, right, is on this field MRAM. Even like IBM's 16 megabits demonstration, right, in the around 2004, 2005. And then the STT-MRAM took off around 2006, 2007, and 2008. So you see the megabit level demonstration from the STT-MRAM. Okay, this is the early days. And the STT-MRAM, the latest, I think the largest is about a few gigabits, okay, today. So let's look at what is the STT-MRAM in more details, okay? STT stands for spin transfer torque. It's a current-driven switching, okay? But the current is flowing through the MTJ stack. So here, we are going to use the current instead of the field to trigger this resistance switching, okay? So if you, for example, apply the current upward, then the free layer, in this case, will point to the left. If you have the current downward, then the free layer will point to the right. Okay. Of course, this current is larger than the read current. Read current, because read, you are going to also read through this stack, but the read current is lower in the magnitude. So here, then you may wonder, okay, why this could help the switching. So here, then this slide explains the detailed physics. It's not very easy, but I try to explain. Okay. So here, the spin transfer torque, that means the spin current is going to transfer a torque to the free layer. Torque means some forces to rotate something. Okay. So here, let's look at what's going on here. So assuming initial state is anti-parallel, so here in this case, the pinned layer always to the left, and the initially free layer is to the right. So what you are going to do is to apply a current downward. Okay, current downward, that means electrons inject the other way, because electron flow, always opposite to the definition of the current flow, right? So electrons, but electrons, there are two kinds of electrons, okay? Because electron will have the spin state. And don't ask me what is a spin. Then it's very complicated to explain. So you have to believe the electron has the spin. There are only two spin states, pointing up and pointing down, okay? Or in this case, pointing left and pointing right. Let me use some incorrect way to explain why there is a spin, okay? Which is incorrect, okay, in physics. If you talk about this in a physics department, then people will laugh at me, okay? But for you to understand, okay, think about the electron, and the Earth is rotating, right? Then it's like electron is rotating. Then from the right-hand rule, you have, if the current is circling like this, you have the magnetization pointing up and pointing down, right? If the electron is rotating clockwise or counterclockwise, then they are going to generate the field, magnetic field pointing down, pointing up and pointing down. It's like the Earth is, rotating, right? Not correct, but that's how you can think of the electrons will have the spin up and spin down. Why electrons will have the magnetic property, okay? So here, there are two kinds of electrons, but in normal material, okay, not magnetic material, the number of electrons pointing up and pointing down, or in this case, pointing left and pointing right, will be equal, okay? You don't see that spin-dependent current in normal material. But in the magnetic material, then the property of this magnetic material, for example, the pinned layer here, is the magnetization pointing to the left. Then it has a property, okay? It will only allow the electrons with the same direction to pass, okay? So this magnetic material will reject in this case, the spin right electrons will be bounced back. It will not allow the opposite directions electrons, if they have the spin towards the right, in this case, will be bounced back, okay? So only the electrons pointing to the left can go through this pinned layer. And then these electrons will turn through to the other layer. So these electrons pointing to the left will insert the torque to this layer's magnetization, okay? So that's why it will, rotate this one, insert of torque, and then finally, this one will flip to the left. Because only the electrons with left spin can turn through in this case. So then if we want to switch back, so initially, let's say if they are parallel, okay. Now you have to apply the current the other way. Or in other words, electrons will inject from the top. So here, the free layer is very thin. So it will allow all the electrons to go through. And then when the electrons, in this case, pointing to the right, after they reach the pinned layer, because pinned layer is typically thick and with a strong, orientation, these electrons will be bounced back because this pinned layer will not allow the electrons pointing to the right to pass through. So this will be bounced back. While those electrons pointing to the left, because all the way they have the same direction, they will go through. So here the bounced back electron pointing to the right will insert the torque to this free layer, and then it will force the free layer to flip to the right. So that's the detailed physics here. So as you can tell here, actually it's not exactly the same. So here, for example, on the right-hand side, this rely on the electrons that it's bounced back. Okay. So that means there's a symmetry in the P to AP or AP to P switching. So actually, if you look at the spec of the MTJ, for example, the switching current or the switching time, there's slight difference, okay, between the rate 1 and rate 0, essentially. There's slight difference because this is not exactly the same. This one rely on the electrons that is bounced back. This one is relying on the electrons going through to change the orientation, okay?
So with pinned layer, does it ever?
Pinned layer never change. It's pinned by design. That means you have to, as I said earlier, right? You say that complex structure that is to stabilize that pinned layer is thick, and then with the help of this synthetic antiferro layer, then it's pinned. Or in other words, in the real operation, your current is not large enough to trigger that change. Of course, if you have a very large current or something, then that may change, or even you put it under like a strong magnetic field externally, like a Tesla, tens of Tesla, whatever, then of course you will destroy everything. I mean, the normal operation, that is pinned.
It happens when the current is very high.
You mean the pinned layer? The free layer? Yes, I mean current high enough.
Then in the field MRAM, we have current going through it, right? So there is no mechanism like this happening.
No, I mean that's different, right? The field MRAM, the current is never going through the MTJ, the right current. Read current is always small. Here we are talking about the right operation, right? Read nothing will change. Read is very, very small, right? So in this case, read current is also small. Read will not change anything, okay? So here when the current is large enough, but this current will be lower than whatever current you apply to the field MRAM. I don't have the number there, but yes, slightly you can check some papers. Not much, a little bit, yeah. This is more physics. So yeah, this is a very intriguing property. Okay, so if you really solve the quantum mechanics, because this one analytically you can do that. The MRAM is well described. The STT phenomenon is well described by the quantum physics there. So, but you can think this is pointing up and pointing down, right? So what you are going to do when you apply that current, you are going to basically rotate this, okay? This axis is pointing up. When you apply current, it starts rotating, okay? And then here, this equation essentially describes the angle, the theta, this angle, as a function of the external field, and then the external current, and some property of the material. So here, this kind of motion or movement in physics is called precession. Okay. I think if you recall your college level mechanics, maybe you still remember something. I don't know if they teach this. Okay. But anyway, this is called precession. So essentially, you are going to rotate this guy. Of course, the larger the current, you're going to rotate more. And then here, there's a thermal aspect. So here, you are going to rotate. But if you withdraw the current, okay, if the current is not approaching the threshold, then this will go back. Okay, it's like you are going to rotate. And if you remove the current, then it will go back. So the MRAM, in some sense, is very similar to the SRAM in terms of the flipping. So SRAM, if you think about SRAM, we have the noise, right? We have the butterfly curve, right? If noise is large enough, then we are going to return to the original point. So the same thing here, the MRAM. If the here is like you apply some current, it's a noise current, not large enough, then it will return to the original point. So, but here, then it may flip if, okay, you are approaching somewhere here, then on top of the current, there will be thermal noise, then it may flip, okay. So here you see that you have the threshold current. But in some cases, you can also flip, okay, if you have the thermal. So this is very complicated. I will skip that, but then later I will explain why this matters, okay. But before that, then let's look at the STT history, okay. So because this is well-described physics here, actually the STT effect was theoretically predicted in those papers first. Some, calculation was done, and then this was predicted, simulated first. And then later, like 3 years later, people experimentally demonstrate this phenomenon. So this is a very good example that how theory can guide the experimental breakthrough. This is not something that you first fabricate and then try to explain with some model. This is you came up with some theory, and then people later try to verify that. Okay. So this was those breakthrough papers with the in that case very simple iron, but later people have used a very complex material. But anyway, so this was the early research, and then let's look at the key metrics we want to evaluate. So first, the JC0. That is a critical current or threshold current to write. So this is the threshold current. Of course, the rate margin is defined by the TMR, the on-off ratio. And then later we'll talk about the thermal stability, because this process will also be affected by the thermal. And this delta is essentially the EA over KT. Okay, the activation energy over KT. And then breakdown voltage. Okay. So there are some equations, we can skip that. And let's talk about some of those metrics. So this is why the precession versus thermal matter. Okay. So here, this is if you measure the STT-MRAM, you'll get this kind of relationship. So depending on the current pulse width, then the critical current JC to trigger the switching will change as a function of the pulse width. So the pulse amplitude versus the pulse width. So here you see that of course, if you want shorter pulse, you have to apply a little larger current, okay? And then here, within a few nanosecond range, it will change from the thermal to the precession region. And after that, it will exponentially increase. So if you want to switch it very fast, then you have to really apply a very large current, because in that time scale, there's less probability for thermal to fluctuate to help you to flip over. But at a longer time scale, then the thermal will help. Okay. But typically, people are operating this near this boundary. Okay, we are not going to operate this within the precession region. Otherwise, the current will be huge. So ideally, you want to reduce the current below to this level. But typically here, the current is like 5-6 mega-amp per centimeter square. So this is current density depending on the area of the MTJ stack. So this area is a current divided by area, this current density. Okay. So you can calculate a little bit. For example, if it's 100 nanometer by 100 nanometer, what is the current? If it's 1 mega, but most of technology today, even from foundry, is larger than this value. Okay, it's not 1 mega. 1 mega is very ideal scenario. If it's 100 nanometer by 100 nanometer, you can calculate the current. What is that? So 100 nanometer by 100 nanometer, right? So you have to convert to, let's say, centimeter. So this is what? Centimeter is like, let's say nanometer to centimeter is 1e7, right? 1e minus 7. Is that true? Yeah, and then this is will be 1e minus 5 and 1e minus 5, right? Is that true? So then squared 1e minus 10, and then times this guy is like 1 times 10 to the power 6 ampere divided by this. So it's 1e minus 4 amp. So it's 100 micron, you see. Even 100 nanometer by 100 nanometer, if the density is 1 mega amp per centimeter square, you have to apply 100 micron. Of course, this is better than the field MRAM like milliamp before, right? So, but still 100 micron, the W over L of a transistor won't be 1. Okay, so then the other thing is the switching, because the thermal vibration, the switching is stochastic. Okay, so if you measure the bit error rate, that means the failure of the switching as a function of the rate voltage, then you will see that if you increase the voltage, that means larger current, then you can make the switching pretty deterministic. But if the rate voltage is small, or the current is slower, then the flipping sometimes successful, sometimes not, right? If you recall that this like precession, and then if you remove the current, then it will go back. That is called the damping, precession and damping. So this one, if the voltage is small, then that means this is not large enough to go through that barrier. But here it may have some like at this point, maybe due to the thermal fluctuation, you may jump over. Okay. But of course, the farther away from here, then you have less chance to flip over, or that means larger error rates, right? So that's why you have this behavior.
The pulse width that is showing is the current pulse width.
Yeah.
But you said if it is in precision,
this is not in the precision region, right?
The 10 nanosecond before shorter pulses is precision.
Precision is typically below like 5 or 3 nanosecond. Yeah. So then retention, okay. The thermal stability factor delta is defined by EA over KT. basically the relative height of this barrier, because you have two states, then thermally you can jump over. So typically you want this delta to be like 40 to 60, okay? Because KT at room temperature, is 26 electron volt, 0.26 electron, 0.026 electron volts, okay, 26 milli EV. So here the EA you want to be larger than like 1 EV, even more than that. So again, you do this Arrhenius plot, 1 over KT plot, then you can get this projected retention time. The same thing. So you bake the sample, right, and measure how long it will take the time to flip. So here then there's a trade-off. Higher, you want lower switching current, but higher thermal stability. In most cases, those two will conflict with each other, right? The higher the barrier, that means more difficult to switch. You need more current to switch. So it's very difficult. So here, what you prefer is in this corner. But in many cases, you will see the trade-off aligned this way. Larger stability, but also higher current. So that's why people define the figure of merit is the ratio of those two. You want smaller this, you want larger this, smaller this. The figure of merit here is the smaller the better. So then the other challenge here is the switching current, but actually from this simple analysis, you see the scaling might help. So that's, for example, if the current density is 4 megaamp per centimeter square, then with the scaling of the technology node, then we are going to have, let's say the dash line is like transistor, because it's only proportional to the width, right? Assuming, let's say the transistor current density is the same for different technology nodes, then the transistor drive current actually will be, for example, let's say, if the JC is 4 megaamp at, let's say, 65 nanometer technology node, you need W over L more than 10 to provide this current. But with 22 nanometer node, you see that here, this squared, because it's an area, you have to scale both, right? F and F for the MTJ. But transistor, you only scale the W, right? Which is F direction. So then at 22 nanometer, you see that here you need 10F. So here at 22 nanometer, you need 4F is enough to provide this current. So it helps, okay, with the scaling. But still, fundamentally, we want to reduce this guy, okay, this JC, towards 1 megaamp per centimeter square. And then the endurance, okay, how many times you can cycle the device. Typically, it's limited by the breakdown of the MgO layer, the peroxide layer. So what you can do is to stress the device, or let's say measure the cycling endurance at higher voltage, higher than your nominal write voltage. You want to stress or accelerate the TDDB, the time-dependent dielectric breakdown. So for example, here you cycle the device at higher voltage, but you have to vary the voltage and get the cycles to break down. So here, for example, at 1 volt, so here we have to, let's say, focus on the tail bit. Tail bit is 1 ppm. It's 1 out of 1 million. If you look at that tail, then at the 3 voltage, you're going to measure how many cycles to break down. So here, for example, you only like 100 cycles. Here, like 10 to the power 6 cycles, then you need to do a projection because the nominal operation voltage is not 1 volt, typically maybe somewhere here, 0.7, for example. So then how do you do the projection? Still, there is a debate in the community. There are two models for the TDDV. One is called E model, one is 1 over E model. So if you do the E model, it will be a straight line here. But 1 over E will, have some curvature here. So even with E model is more conservative, then you see that here, maybe 10 to the power 10 cycles for the tail bits, the worst bits, okay. So this is how you do the projection, because nobody can measure like 10 to the power 14, 15, 16 cycles. This is where we wish to get, but if you want to measure that, you wait 10 years and it's impossible. So this is how we do the projection of the endurance. All right, so here we just simply compare and have to speed up a little bit. So actually within the STT-MRAM, there are two flavors. One is called the in-plane, one is called the perpendicular MTJ. In-plane is what we discussed so far. So here you see that mechanization is pointing left and right. But then industry nowadays is using this so-called perpendicular MTJ. So here in this kind of MTJ, then this mechanization is pointing up and pointing down, even in this thin film. So the mechanization is pointing up and down, okay. So this one will help with the scaling, especially in reduce the current, switching current. So we will talk about that in the next. So here, so far we talk about this in-plane MTJ, but now we will look at the perpendicular MTJ. So here the hard axis essentially is vertical in this case. So why? So here, if you look at the in-plane MTJ, if you want to make it stable, you need to make this kind of a anisotropic in the structure. So you need to make it more like a rectangle, right? You magnet. If magnet is let's say circle, then the direction, there's no preferred direction. You can rotate to any angle if it's in the plane. So that's why you need to make the shape to be like this rectangle, or let's say, yeah, you need to have some and like the ratio, okay. So then this will limit the scaling, okay. But if you have the perpendicular one, so then you are going to have this, you can have the circle one, because this is pointing up and down, okay. So here then, this will help with the scaling. So here, there's another explanation why this is more efficient. So in the in-plane case, okay, because here the precession and the thermal path is separate. So in the spin transfer, the torque is going to flip this actually along this trajectory. And the thermal is going to do that in this or in plane, okay. But in the vertical case, both of them will have the same kind of path. So this is more effective. So anyway, so now industry switched to the perpendicular MTJ, and then there are many challenges still there. So I skip the details. But one of the challenges in the real fabrication is if you want to scale the technology, the key challenge is here when you etch the structure, the sidewall is a weak spot. So many leakage paths and the defects is coming from the sidewall when you etch the entire stack, because you deposit those films, but you need to make isolated cells. So you etch. Once you etch, then this edge becomes a weak point. So let's look at some of the early demonstrations for the STT-MRAM. So this was by a small company called Grandis in the early 2010, around that time. Later, this company acquired by Samsung and become Samsung's STT-MRAM technology, essentially. So this was at 19 nanometer, 256 kilobit test chip, and rate current about 200 microamp, and the speed about like 20 nanosecond, endurance 10 to the power 13, okay, 1T1R. And then this is underlying transistor. This is at metal 4, metal 5. So with this kind of array, you have to test this resistance distribution. Because cell-to-cell variation will give you this resistance distribution. You see that here, the low resistance state around 2 kilo ohm, high resistance state around 4 kilo ohm. Then the TMI is about 100%. And then you have to make sure that there's enough gap in between, right? 3 sigma distribution. You have to look at the gap, okay? Overall, the margin is pretty small, okay, compared to other technology. If you recall, like R1, phase change could be like 5 times, 10 times, or even 100 times. So here is only 2 times in terms of the ratio of the resistance. So that's why MRAM's design, especially the sense-amp design, is more difficult because you have to compensate for this small ratio. And then here's the endurance, right? So you have to measure the breakdown as a function of different rate voltage. And then here is log cycles. That means 10 to the power 7, 10 to the power 8, 10 to the power 9 cycles. Of course, there will be variation from cell to cell. So then you get the median value, and then you do the extrapolation using the E model, for example. That's why they conclude that, okay, they can get 1E16 cycles at the operational voltage at 0.6 volts. But actually, they only measured up to like 1E11 in real tests. So here, there are some recent updates in the recent years. So there was a group at Tohoku University in Japan, which made a lot of contributions to this field. I know the Professor Endo-san. He is regarded as one of the pioneers in the STT-MRAM. And so anyway, the Tohoku University has demonstrated many interesting STT-MRAM device and also chips. So here, this was at IDM 2018. It's like a 40 nanometer CMOS, underlying CMOS, 1T1R. And then here is 128 megabits, okay, from the university, okay. And then here the cell size, 0.4 by 0.4 micrometer square. And then you see the rate latency around like, depending on the voltage, around 10 nanosecond or so. Endurance larger than 10 to the power 10. And then retention, 85, 10 years, of course, extrapolated. So then around 2018 and 2019, around that time, all the major foundries announced that they commercialized the STT-MRAM, okay? So here, this is from the Samsung. So you see 1 gigabit in 28 nanometer node. And then here, those numbers. And the cell size, 0.03 micrometer square, right? A little bit larger than 3 nanometer SRAM, a little bit larger at 28 nanometer node. And then TSMC, here 32 megabits at 22 nanometer node. And then here the latency 10 nanoseconds. But then the endurance, you see, is only 1E6 in this case. And the Intel also. So actually, in Intel's demonstration, they showcase 2 versions of the STT-MRAM. So here, the only difference is that the MTJ size is different. So because they want to differentiate those 2 applications target, one is eNVM, This is like the embedded non-volatile memory we talked about before for the eFlash replacements for the microcontroller and so on. So in that case, you need retention. So that's why here the diameter of the MTJ is larger, like 70 to 80 nanometer. So you can make the magnetic orientation more stable. But here the STT-MRAM could have potential to be used in the last level cache, like L4 cache, because the speed could be a few nanoseconds. So then if you want to make it L4 cache, you have to size down the diameter, make it easier to flip. Therefore, you can write it faster. But in that case, then the retention will sacrifice. So this retention will be only seconds. Okay. So you can tailor the technology for different applications. So anyway, to summarize, okay, today the major foundries have all the STT-MRAM commercial products already. Most of them are from 28 to 22 nanometer nodes, including TSMC, Intel, Samsung, Global Foundry. Okay, they all offer STT-MRAM. This is like widely available compared to other ARM, phase change, Ferro. Only some of those companies are offering, but MRAM, STT-MRAM is kind of universal there. So here I just summarize some of the recent publications from the IEDM and the ISCC. So I will not have time to go through the numbers. If you are interested, you can look at the numbers in terms of the resistance, on-off ratio, cell size, and then the latency, endurance, retention, right? So here I just want to emphasize, if you are targeting at the eFlash replacements, so what you care about is this retention, okay? Especially for automotive, you need to have like 150 degrees C, like years of retention. So in that case, the endurance sacrifice, typically 1 million cycles only, okay? But this is good enough for the eFlash replacements. If you really want to use it for the last level cache, you need endurance, even more than this, right? You need like even 1E14 endurance. In that case, you have to sacrifice the retention. You see the retention degrade to like seconds or minutes in those cases. So here, as I said earlier, Intel just changes the cell size. They can satisfy 2 applications on the same platform. Okay. So here, I just want to showcase some latest progress. So this is the recent data at this year's ISCC, TSMC, demonstrate the 16 nanometer FinFET node STT-MRAM. So here, the MTJ is at between metal 4 and metal 5, and then this is you look at the spec. It's more like a last level cache spec, right? So here the retention is only 1 millisecond, and then the endurance is high. Of course, TSMC also has the eFlash version of that. Okay, I think they published it a bit earlier than this year's ISCC. And Samsung also showcase their 14 nanometer MRAM. Okay, so here, I think if I recall correctly, in this work, to my surprise, Samsung seems managed both eFlash and the last level cache within the same platform. So in this particular design or this technology, you see that the endurance 1E12, retention also 10 years. At least this is my first time I see that good endurance and good retention simultaneously reported by a single design from this Samsung paper. We will say 24. It's amazing to me. So Yeah, if I look at this year's IEDM agenda, because I was in the TPC reviewed all the papers. So I remember there was one paper from Samsung, I think, scaled the STT-MRAM to like a 10 nanometer or 8 nanometer node. So that is the latest progress. It's not published yet. So, IEDM is 2 weeks or 3 weeks from now. But I reviewed that paper because I'm the TPC member. But the latest progress is that this technology could scale to potentially 7 nanometer. Actually, that is on the roadmap for Samsung and TSMC. So last few minutes, we're going to quickly go over the third generation of the MRAM. This one is still under development. There's no commercial offering yet. This is called SOT. So SOT is a spin orbital torque. Spin orbit torque. Okay. So here the difference is that they want to decouple the read and write path. This is actually similar to the field MRAM. So we are going to have an underlying right word line. So the difference is that in the field MRAM, this underlying word line separates from the MTJ. Right, separate. You are relying on this. There is a dielectric in between. This is separate in the field MRAM. But in this SOT-MRAM, this is adjacent to the MTJ. There's no separation in between. There's no isolation, whatever in between. So this SOT metal is contacting with this free layer. In this case, the free layer needs to be attached to this metal. Okay, so that's a difference in terms of structure. So here then there are different types of the SOT-MRAM. I will skip the details depending on the orientation of the the magnetization versus the spin, the SOT channel direction, or let's say this red current direction. There's XYZ type. For example, the Z type is the perpendicular MTJ adjacent to this SOT metal. So the benefits of this one is read and write is decoupled, because in the previous STT-MRAM, you mentioned the problem earlier, right? The read current is also going through the MTJ. So then there might be the disturb, right? So here, then you want to decouple the read and write path. So here we can do this. So here, this red current is going to generate that field, but this torque is going to generate the torque. The torque is inserted to the free layer due to this spin orbital effect. Again, it's quantum mechanics. We will not go into the details. But here the advantage is that this switching could be pretty fast, even faster than the STT. So STT we said a few nanoseconds. This one could be below 1 nanosecond. Okay. So here then there's a challenge for this design, because we have to break so-called the symmetry in the structure. That means in this design, we need external field to trigger this one, at least for the type X and Z. We have to break the symmetry. So that means we have to apply external field. So anyway, so here this was a design proposed by Tohoku University. Endo-san is a very famous professor in this field. So here this point, this canted cell. So here again, they play with the direction. So basically, this hard axis is not in parallel with this SOT metal. You have some angle. So this angle help to make it external field free. So you can switch the MTJ by changing the current direction only in the SOT metal. So here they demonstrated, here the like a 300 picosecond switching. So this is pretty fast. And here is a summary of the SOT-MRAM from their tutorial, you see the specs from this candidate cell. The smallest you can demonstrate 9.3 nanosecond, and also from iMac, they also demonstrated 0.3 nanosecond in the SOT. But still, the current is pretty large. So you see the current, this number. We need 1 megaamp. This is like 20 or even 100 megaamp. It's still far away from any practical application. Even though this one could be faster in principle, then the current density is still too high. It's very power hungry. So I don't see the commercial benefits right now. Okay. So here's a chip level demonstration. And yeah, I'll skip that. So here, this is a summary of this MRAM. Again, STT-MRAM is right now commercially available from all the major foundries with a scaling roadmap to 7 nanometer and even beyond. And the SOT is still at early stage, even though it has a potential to be very fast memory. The only candidate that could have the same speed as SRAM. However, the SOT's write current or write power is still orders of magnitude higher than SRAM. So that's the status of the MRAM technology today. All right, I will stop here.